Okay, so today the first set of problems that we will do are based on moments about an axis, and we discussed in detail what we mean by moment about an axis. Essentially, you are supposed to find out the normal distance to the force, but then from the axis. Okay, so you need to identify a plane, but then for any given axis, the only part of the force that can cause any amount of moment uh, would be the one that is uh, that is that is normal to the axis. So essentially, you are supposed to take a plane that is perpendicular to the axis itself. Okay, and there you are supposed to take the projection of the force, and essentially we showed that what we mean by moment about an axis is essentially the moment due to this projected force. And then we can take we can take any point, the point of intersection of the axis with the plane, and that would serve as the reference point for the moment. And we showed that reference force can be anywhere on the axis, because this plane is arbitrary. No matter where on the axis do you take this perpendicular plane and take the projection, you're always going to get the same force. So that reference point can be anywhere on the axis, and essentially the moment due to this projected force is essentially take an arbitrary point on the axis, let's say O, and take another arbitrary point on the force line of action of the force. So essentially you have the position vector rp with respect to O. So you take the moment of the force F about O, and that would be the moment about O should be this is a total moment about O about any axis. Okay, now this moment is a vector and it has its own direction, but we are only interested in the component of the moment that is along this axis. Okay, for example, if I think of this as the uh, plane of the position vector and the force, so the moment would essentially be normal to this plane, right? So but it's not the total moment that I'm interested in. So this is the moment due to O, right? Sorry, it is the moment about O due to that force over there, so which is again the position of P is arbitrary, as we know. So but then again the position of O is arbitrary when we are doing this. Let's say this is the unit vector along the axis. Let's call this AA axis. So EAA is the unit vector. So moment about EAA or AA axis is essentially EAA dot. Okay, and this essentially is a scalar triple product. Sorry, this is the scalar value or the component of the moment that is along this axis. And if I were to represent that as a vector, so I should again multiply it with a unit vector. Okay, and that essentially gives me the direction of the moment. Rest of the moment due to this force about this point is essentially perpendicular to the axis. Okay, and that's not the part of the moment that is about this axis. So it's only the parallel part. And and what else? And yes, so this essentially is the scalar triple product. The scalar value of the moment is essentially the scalar triple product of these three vectors, and it essentially represents, let's say, if I join the tails of each of the vectors, so this is rp, this is f, and let's say this is EAA. So essentially the parallelepiped formed by these three directions Actually, this line should be solid. Okay. So it essentially represents in some space. Okay, this would represent the volume enclosed by this parallelepiped, this scalar triple product right here. And because of that, it can be from this diagram. It can be shown that this is also equivalent to if EA RPO, or it can also be shown as RPO if EA. So scalar triple product have this chain rule that can be used. But if I break the chain and if I just simply alternate the spaces of two vectors, I would get a negative value. And on this negative value, if I use the chain rule, I'll always get the negative value. So that is there. What other properties of scalar triple product are there? For example, since it represents a volume, okay, if the third vector is coplanar, okay, that means if is not equals 0 vector, if any of the alpha i's is not equal 0, that means this sum should be 0 for trivial values of alpha 1 equals alpha 2 equals alpha 3 equals 0. And if that is the case, okay, we have the scalar triple product as a non-zero quantity. Whereas if it is possible to represent with non-zero alpha I values, at least one of them being non-zero alpha I values, that this sum equals 0, okay, then actually the third vector, if we take any two vectors, the third vector is coplanar, and therefore the volume enclosed would be 0 and the magnitude of the scalar triple product would be 0. The term used in linear algebra is whether or not the three vectors are linearly independent. So this is what is meant by linear independence. If they are linearly independent, the scalar triple product right here would be non-zero. Okay, so so we have discussed this.
Sir, sorry to interrupt, but I think someone are waiting.
Okay. Okay, so what else? Yeah, you already know this, that I can represent the scalar triple product as a determinant of this matrix whose rows or columns are represented with each of these vectors right here. Okay. So this your scalar triple product right here can also represent this determinant right here. So yes, all of these are properties of the scalar triple product, but we only need it to get the moment about an axis. So for that, we would look into the problem number 41 and problem number 42. Okay. So let me explain what is happening in problem number 41. So there is a lever which you can try to rotate by applying a given force, but that lever itself is only free to rotate about y-axis. Okay, so any moment that you apply, okay, which is not about y-axis, So that is not completely utilized. Okay, only the part of the, because unless of course you break this support, which is a uh, mm, which only allows the rotation about y-axis, unless of course you break this. Okay, you there is no way you can rotate this handle over here about any other axis than y-axis. Okay, so if the moment degenerated due to the force is not about y-axis, then that moment cannot be completely applied. Okay, and that's why we need to figure out how much of that moment, or let's say this force right here, the 16 Newton force right here. Okay, so let's look at the problem. The 16 Newton force being applied at so and so location. Okay, so 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 that moment, for that moment we need to figure out how much of that moment is about y-axis. Okay, so we would use the formula that we have just learned. Okay, so I need you to try to get the moment about the axis. Okay, first with respect to point O right here, and then about point A right here, and check whether you get the same moment value. Okay. So first try to get the moment of this force. Okay, let me tell you, this force is lying on a plane which is parallel to xz plane. Okay, it's not mentioned, but it is apparently a plane parallel to xz plane. So the force only has components in z and x. Okay, and that plane is situated 50 millimeters away from the xz plane, and vertically it is uh, it is below the xy plane. Okay, it is below the xy plane. How much is it below? That you can figure out from the length of this handle and the angle that it makes with the x-axis. Okay, this handle itself is on the xz plane. Are you able to start working on the problem? What is the position vector with respect to O?
So that is the point of application of force.
Yes, that of the point of application of the force.
Uh, it would be in the y-axis. It would be means
Sorry,
plus plus 200 j cap, and
plus 200 j cap.
it's in the y-axis.
No. You see that
And
200 millimeter right there. Let's say if I try to get it from with respect to point O right there. So with respect to point O, okay, let's just start working on it. So again, the force lies on a plane which is parallel to xz plane, but it is in front of xz plane. So let's say this is the force F being applied to the handle. Okay, and I'm interested in finding out the position vector of this point, and let's call this point as C. Okay, so this point is B. Now this B point right here, we can try to get okay, so this is x-axis, and this is the y-axis, and this is the z-axis. Okay, so again, so the position vector of B with respect to O should be, so this length is 200. Okay, so if this angle is 45 degree, this angle is also 45 degree, which basically means RB with respect to O should be let's say 200 by root 2. So that's I minus 200 by root 2 k cap. Okay, now that is the position vector of B. Okay, now to go from B to C, you need to move parallel to y-axis, parallel to negative part of the y-axis. Okay, so I can now try to find out RCO, and that would be RBO plus or minus 50 JK. But let me tell you this, because we know that we are free to take any arbitrary point on the axis. What I would do is I would take a point which is 50 millimeters ahead of point O and is on the y-axis, which basically means, let's call that point D. So basically RC with respect to D would be RB with respect to O. Okay, and F right here makes an angle of 30 degree with the positive x-axis and lies on a plane which is parallel to xz plane. So F is going to be minus 16 times root 3 by 2 I plus 8 k cap Newton, and these are all millimeters. Okay, so what you can do is you can try to get the moment of the force about point D, which would be cross F, and then take dot product of the same with J. So my, so basically moment about y axis or y component of the moment, okay, is going to be J dot this moment right here. And you can check whether you take point O over here or D over here or some other point A over here, you are always going to get the same value of y component of the moment. Okay, moment about a given axis is essentially the Cartesian component of the moment in that axis. Okay, so first calculate the moment about point D.
Sir, the answer is coming 828.16 Newton millimeter.
Sorry,
Sir, the answer is coming 828.16 Newton millimeter.
828.
0.16.
Okay, so you're saying this much Newton millimeter.
Yes, sir.
Let
Yes, sir.
someone else also calculate. Let someone else also calculate. Let's check how much is the moment.
ওটাই মাইনাস হবে না?
Depends on whether
No,
you are taking J or minus J.
মাইনাস যে আসছে আমার অ্যাকচুয়ালি।
No. The point is whether you are taking dot product with J, whether you are considering the axis to be y-axis or negative y-axis.
Oh, I considered is as J.
Okay. Uh, if you consider that to be axis to be J, I think you should get a negative sign. Oh, sorry. I think you should get a positive sign
Yes, sir.
because
If
the
I
moment
consider
should
the
be
positive,
about y. Yeah.
Are we considering the negative y-axis as the axis?
Yes. And how do I know that it is supposed to be so? For example, if I look at it from the negative side of y-axis, so this is how the projection looks like. So this angle is 45 degree, and this force makes an angle of 30 degree. So if I extend the line of action of the force, this is going to be the situation. Instead, if the force was acting at an angle of 60 degrees, this is what the situation was supposed to be. Okay. So if you really think about it, this kind of force
That's a positive
would try to
axis.
rotate the system about y-axis. So you're supposed to get a positive my.
Positive axis.
Okay. Okay. So let's then focus on the next problem. তোমাদের কি আজকে কোনো ক্লাস ছিল বা ক্লাস আগামীকাল কোনো ক্লাস আছে বা অ্যাসাইনমেন্ট কিছু? আজকে অ্যাটেন্ডেন্সটা তো কম কেন?
কালকে পরীক্ষা আছে আমাদের।
হ্যাঁ, সেটা আমি কিছু অ্যান্টিসিপেট করেছিলাম। কি পরীক্ষা গো?
ই ল্যাবে।
lab.
sir, lab আছে।
আচ্ছা আচ্ছা, ওকে। In that case, we will consider just one more topic today, and after that we will end the class. Achha. So, okay. So look at the next problem. Now, what is being done? You see, this door is being pulled from one of its corners. Okay, and so that point is A, and this point B over there.
স্যার
দেখা যাচ্ছে না?
আপনার এটা হোয়াইট বোর্ডটা খালি খোলা রয়েছে আপনার।
আচ্ছা, এবার দেখা যাচ্ছে?
না স্যার।
না
No, sir.
Okay. পুরো স্ক্রিনটা শেয়ার করলে প্রচুর মিররিং হয়। Okay, so you're talking about this door right here. So you see it is being pulled from one of its corners, and this point B right there is on the wall. Okay, and that wall is actually your exit plane. Okay, and as you can see, the door can only open about x-axis. So yeah, of course, this is not the problem statement. Okay, the problem never mentions that the door can only open about x-axis, and that's why you are supposed to find out the moment of the component of the moment about x-axis. The problem simply asks you to figure out how much what is the moment about x-axis due to that force. Okay, and to be frank, at this stage of our course, we shouldn't be bothered about what is the reason behind asking such a question. Okay, we should be only enabling ourselves to be able to answer that question. So just don't overthink this. Okay, but it's quite evident why you are being asked to find out the moment about x-axis. It's because the rest of the moment cannot cause any amount of rotation. I mean, you cannot make it rotate about y or z axis. Okay, unless of course you break the hinges. Okay, so keeping them intact, you can only rotate it about x-axis. So that's why you are being asked to find out the component of the moment about x-axis. Now, you see the force, unlike the previous example, now has a reference to 2 points, point A and point B. Okay, now I would ask those who have even roll numbers, okay, try to get the moment about x-axis by considering this corner point right here. Okay, can you see my cursor?
Yes, sir.
Yeah, the point on the axis of the door which is nearest to A. Okay, and consider point A, okay, for the position vector. So try to get the moment about this point and then try to get the moment about the x-axis. Okay, and the ones who have odd roll numbers, okay, take the origin for position vector. Okay, let's call it O, and let's call this point as B. To try to get call this point as C. So B point is already there, and closest to O would be B. Okay, it is easy to get the position vector of B. So try to get the position vector of B with respect to O. Okay, and of course, how do you get the force? That process remains the same. You get the position vector of B with respect to A, get the unit vector, multiply that to the magnitude of the force, and you have the Cartesian form of the force. So that process is same. I'm just asking you to calculate the first moment, okay, the moment about the point on the axis. Okay, so you can use two different methods. Those with even roll numbers take this corner point of the door, and those with odd roll numbers take the origin, okay, and point B for position vector. Okay, and see what sort of answer do you get. By the way, what are the dimensions? So the door is tilted by an angle of 15 degrees. Okay, and you see y coordinate of A is not 1 meter. Although this says 1 meter, that is actually is the width of the door. But when it is tilted by an angle of 15 degree, when it is making an angle of 15 degree with y-axis, so its z component is sine 15 degree in meter, and the y component is cos 15 degree in meter. Now, of course, cos 15 degree is very close to 1, but that essentially is the y component of the coordinate. X component, however, is 2.5 meters. Okay. So just be careful with getting the coordinate of point A. 1 meter is the total distance from the x-axis. So I'm kind of trying to draw the door here. Okay. So this is your x-axis. Is the this is the z-axis. And this angle right here is 15 degrees. This is a point B. So this is your 200 Newton force. This is the origin. Let's call this point as C. So, and this point is A. So we could be trying to get the position vector of A with respect to C.
Sir, one question, that point B is directly above the x-axis.
Sorry,
That
what
point B
Huh?
is directly above the x-axis.
Uh, I would give you more clarification. It is on the xz plane. Okay, so this coordinate right here, 0.5 meter, is its x
Yes, okay, sir.
coordinate,
Yes, sir. That is
and
what I thought.
this coordinate right here is a z coordinate. And what about its y coordinate? It's not there. It's on the xz plane. So y coordinate is 0. Okay, so if I would like to get RBO, that is 0.5 I plus 2k meter. If I'm trying to get RAC, that is how much? (2.5) for X, for Y cos 15 degree, for Z sine 15 degree, all of this in meter. And if I'm trying to get, the position vector of A with respect to O, so for that I will simply add 2.5 I. Oh, sorry. This is, yeah, this should not be there. So I would simply add 2.5 I. Why do I need that? To get RB with respect to A. And that would eventually give me the unit vector along the force. And the force vector is the magnitude of the force times the unit vector. Now you can get the moment of the force about point O, and for that simply do this, and or you can get the moment about C. For that simply do this. Okay. Just check, in either case the x component of the moment is the same.
Sir, I am getting a 136.91.
Okay, so moment about x, you're getting 136 point.
91, sir. I cap.
Newton meter, right?
Yes, sir. Yes, sir.
Okay. So you took the moment in which method? About O or about C?
No, sir. About C.
Okay, so this one. And has somebody taken with respect to O? Has anyone tried getting the moment about O?
Yes, sir. Doing so one. Sir, I'm a little bit confused. For about O, the axis will be the x-axis.
Yeah, I only want the X component of the moment.
Yes, sir. Yeah, I'm getting 143.2.
140.
143.2.
One, I don't have the answer. You can just tell me. Just
143.2, sir.
143.2.
Yes, sir.
Okay. So, um, so you have tried to get it with respect to O. Okay. Try to get it with respect to C. So, if you have earlier got it with respect to C, now try to get it with respect to O. And if you had earlier tried to get it with respect to O, then try to get it with respect to C.
Sir, the answer should be same in both the case, because while taking the scalar triple product with the R vector, it will what is the value of x at the R vector.
Yes, we have showed that we are supposed to get the same value, but are you getting the same value? We have proved that
Yes,
in
sir.
the
Yes, sir.
previous. So if you are taking moment with respect to C, are you getting the same x component? As with respect to taking the moment with respect to O. So are you getting the same value in either method?
Sir, I am a little bit sorry, sir. It will be minus. Sir. I forgot the minus sign.
In which one?
Sir, my one was with respect to O. With respect to it, will be a minus sign.
Okay. Okay. It doesn't seem to give a moment.
Sir,
negative x-axis.
minus will not
It looks like the moment would be about positive x. You see, the force is above x-axis, right? So, and going from right to left. So it would probably be giving a positive moment about x-axis. Okay, I can tell you why is it taking why you are taking so much time. It's because what I think that in school level you have hardly done any 3D problem. Okay, and in this course we would be doing plenty of 3D problems. Okay, that's what our main focus is, three-dimensional problems. So I would suggest you to make yourself familiar with the 3D geometries and three-dimensional problems, and the only way to do that is to practice more. For all the chapters that we have covered so far, okay, all the sections that we have covered so far, practice more and more problems. Okay, as many problems as required for you to be very comfortable with the three-dimensional problems. Okay, you might be knowing a lot of concepts. Okay, but at the end of the day, you should be also in a position to do the math. So, I mean, we know that we are supposed to get the same answer from either case, but so far none has been able to give me same answer for both cases. We can do all the proofs all we want, but at the end of the day, we still need to practice a lot of problems. And yeah, in the class I cannot show a lot of problems. Okay, so I can only show a few sample problems, but you need to practice on your own. Anyways, so let's move on to the next topic. Okay, and this is our first step into equivalent force system. Actually, I'm not going to equivalent force system today, but this is the first step, and that step is known as couple or couple moment. Okay, or moment due to a couple. Now, what is a couple? Imagine this body right here. Okay, so imagine there are two forces that are acting on it. Both have the same magnitude. Okay, they are parallel and directed in opposite directions. I mean, the sense is opposite. That is, if I consider one of them to be plus, the other one can be considered as minus. Okay, and they do not act along the same line. We know what would happen if they were to act along the same line. If they were to act along the same line, equivalent of that would be having no force at all. Okay, because we are talking about rigid bodies. Okay. Have we been talking about deformable bodies? Then you can think of you have a piece of rubber and you are trying to squeeze it from either side. Okay, with the same amount of force acting along the same line but in opposite direction. Okay, so there is no effect. I mean, equilibrium wise there is no effect, but it is deforming. But for a rigid body, it is absolutely no effect if they were to act along the same line. Again, I just mentioned that word equilibrium right away, but we would not be talking about anything related to equilibrium until and unless we reach there. And before reaching equilibrium problems, we should be, very comfortable solving equivalent force system problems. Okay, and a lot of times you confuse problems from equivalent force system with those in equilibrium, and that's a terrible mistake. That is unforgivable, and whatever marks would be deducted, should be deductible, should be deducted. Okay, so now imagine if the lines are parallel, okay, but they are not the same line. So there is a distance d between the two. Okay, a normal distance, which basically means on the line of action of one, I can take an arbitrary point A and then drop a perpendicular on the line of action of the other. That distance is d. Okay, so if I were to, that system in a sense equivalent to having no force but a single moment, and that moment, okay, has this magnitude d times f, and also is perpendicular to the plane of the two parallel forces. Okay, so so this moment is called a couple moment. Okay, what is the difference between moment due to a force or moment of a force and a couple moment? When we are talking about moment of a force, okay, then there is a single force, not a couple, and the moment is associated with the force. Okay, for example, if this is the force F, then I need to
Moment due to
mention,
a couple is free and moment due to a force is sliding.
yes, moment due to a force, yes, is a sliding. So that is not good enough. Okay, we need to mention a point about which am I trying to get the moment. Okay, yes, you are correct that now if I draw the line of action of the force, line of action of the moment, then I can show the moment anywhere. But showing the moment anywhere on the axis, okay, doesn't accomplish anything. Showing the force anywhere on the axis does accomplish anything, which means that I can take the position vector of the force by taking any point on the line of action of the force. Okay, I can consider the force be acting over here or maybe over here. Okay, so on a rigid body, I can do that. Okay. But yes, saying that the moment is sliding doesn't accomplish a lot of things. But yes, you are correct in the sense that I also need to mention about which point am I trying to get the moment. Okay. Uh, Now, why is it important to find out this net effect? This net effect due to a couple of forces, let's say, okay, is in a way we are trying to get an equivalent force system. Okay, just I said that it is like the first class on the equivalent force system. Okay, an equivalent of this is having no forces. An equivalent of this is having no forces but a moment, a couple moment. Okay, now I showed this force with a line. But the fun thing is this force doesn't have a fixed line. I mean, it has a fixed magnitude for a given set of forces. It has a fixed magnitude and a fixed direction. Okay, but that's it. The two basic requirements to represent a vector. But other attributes of a vector, it's a point of application or or uh, line of action. Okay, those two do not apply to a couple moment. Okay. So how so we can evaluate that, okay. And that we would do in terms of any in terms of three-dimensional problems. Okay, although the diagram may look 2D, but the derivation we are about to do is 3D. So we can take any arbitrary point O, and I chose to do that within the domains of the geometry. Okay, but you can do that anywhere in the universe, and this is the result that you are going to get. Take any arbitrary point B on one of them, so you have RB, and on one of them take any arbitrary point A, so you have RA. So moment due to the two forces, summation of moments about O would be RA cross minus F plus RB cross F. Now, since cross product is linear, this turns out to be RB minus RA cross F, which is RB with respect to A cross F. Okay. Now, RB cross F is, sorry, RBA. So this vector is RBA, position vector of B with respect to A, cross F is also the moment due to the force F with respect to A. And how much is the moment due to this minus F with respect to A? That is 0, because minus F directly passes through A. So this is also the moment of the two forces with respect to A. And for that matter, you can take this point O, this arbitrary point O, anywhere in the universe, okay, and you are still going to get the same moment about that point, okay, which means unlike the moment due to a single force, for which the specification of the point was extremely important, for a couple moment I don't have to specify the point of application, okay, which means I can show this moment, okay, with a given magnitude and the direction using this line right here, or maybe even this line right here. Okay. So it doesn't matter. I can choose any set of parallel lines. And that's what makes this quantity, this couple moment right here, okay, a free vector. Okay. That is the true meaning of the word free vector. That means it has no fixed line of action. Even a force on a rigid body has a fixed line of action, but not a fixed point of application. Okay. But the moment is free, completely free. It can act, the line of action can be shown anywhere. Okay. But that can be a little confusing. That means you can ask, then if the object is allowed to rotate, which axis does it rotate about of all these parallel lines? Okay, the answer is, let's say this is our rigid body, and let's say this is where I pivot it. It means, let's say there is a wall behind it, and I simply made it into a compound pendulum. Okay, so I have put a pivot right there. So it is only allowed to rotate about this axis. Okay. Then if I apply a couple, then this object can perform rotation about the axis of the pivot. Okay. Now this pivoting location is arbitrary. Okay. It can be anywhere. I mean, I can choose to put the pivot anywhere, and for any pivot location, the same moment, because of these two forces, same couple moment would be there. Okay. Typically, this is the idea that once you have a pivot point, you try to get the mass moment of inertia about that pivot point. I'll call that pivot point as O. Okay. So I try to get the mass moment of inertia about that pivot point times the angular acceleration is the moment about that pivot point. Okay. With a couple acting on the body, this couple the moment would be about any arbitrary point, as we discussed, is this couple moment. Okay. Now you see, depending on where do you pivot the object, okay, you understand what is pivoting. You know, you take this to the this rigid body, and you simply put a nail through it, okay, and made it like a compound pendulum, so it can oscillate like this. Now, depending on the location of the pivot, the mass moment of inertia of the geometry, which essentially is take any differential mass over here. The distance is, let's say, rho. So integration rho square differential mass over the total mass, okay, is your mass moment of inertia. But that would change depending on which point do you choose as the pivot point. So this quantity varies. This quantity doesn't. Okay, and the angular acceleration therefore would depend on which point do you choose as the pivot point. MC remaining a constant. Okay, so that's what is the significance.
Sir,
Yes.
স্যার আমরা যদি কোনো পিভট পয়েন্ট না থাকে তাহলে আমরা
যদি ফ্রি হয় ওকে,
তাহলে লাইন বাইন্ডিং দ্য টু ফোর্সেস ওটার মিডল পয়েন্টটা অ্যাক্সিস অফ রোটেশন হবে তো
middle point. Okay, I am not quite sure what you mean by a middle point. I mean, yes, you can define something called a centroid. Okay, you can define something called a centroid. Sorry.
পয়েন্ট বলছি
স্যার দেন
শুনতে পাচ্ছি না
স্যার আমরা কি এরকম ভাবে বলতে পারি না সেন্টারে ব্যাপার জানি না বাট can we say that it will be rotated about the axis which has the least moment of inertia?
Yeah, and that will be symmetric if the body is symmetric.
You see, this is the idea. Problem here is we are here only trying to look at a couple moment, just a single couple moment. Okay. And for some reason, we'll have to think about what is the effect of the moment due to a couple or moment due to a single force. Okay, and there we are not thinking only in terms of equilibrium. Okay, now ekটু শোনো. So although the equilibrium of rigid bodies is covered in our curriculum, okay, dynamics of a rigid body is not a part of our curriculum for this subject. Okay, but every year I have tried a lot, okay, but I couldn't keep discussing what I am about to discuss. Okay, and that is, let's say an object is in 3D, it is free to move. Okay, and there are n forces. Okay, and there are different forces, F1, F2. Okay, and this I ranges from 1 to n. And similarly, there are couple moments acting on the body, multiple of those. So there are MCJ or J ranging from 1 to M. This is a general situation, right? Now you can argue this couple moments are formed by some forces. Okay, but once you have, couple moments are formed by a set of couples. Yes, you can represent everything in terms of forces. But the thing is, once you have got the couple moment, okay, once you have a couple and then you have calculated the couple moment, it doesn't matter whether these two forces, imagine they are on the plane of paper, form the couple, or these two forces. The direction of the forces and the distance or actual distance between the forces, none of those matter. Okay. What matters is the net effect, which is the couple moment. Now, there is, of course, this law you all should be familiar. Okay. This is second law of motion. But when it comes to rigid body, then this expression has a change. This law is proposed by Sir Isaac Newton, of course, but that law right here is only valid for particles, right? So when you are trying to use that for a rigid body, you'll have to understand that not each point in the rigid body is equally accelerated. I mean, if all the points were equally accelerated, the rigid body would only be doing translations. Since it's not, since it is also rotating about some axis or other, so there has to be only one representative point. And that representative point happens to be the center of mass. Okay. So this is the final expression that you get of a very long derivation. Okay. That is included in the, second year, second semester of mechanical engineering students. Okay. But for some reason, we'll have to discuss that today. And then when it comes to the net moment, now the net moment is, of course, summation over I, Ri, if I. Okay, so net moment always is about a point. Okay, so let's take that point to be O. Okay, so when there is F1, there is R1. Okay, and then this other sum with respect to J, so that is on couple moment. That is the net moment about O. So you take all the couple moments and moment due to each of the forces. And this may or may not equal to moment of inertia about O times the angular acceleration. Yes, this is true. This may or may not equal to. And this only works, I mean, the equality only holds for only a special set of points. What are those points? Number one is center of mass. Number two, a fixed point in the space. Number three, a point maybe not fixed, but moving with a constant velocity, that is, no acceleration. Number four, a point need not be the center of mass, need not be the fixed point, need not be even moving with a constant velocity. It is accelerated, but accelerated towards the center of mass. That means, let's say, this is the center of mass, C. Okay, This is the point that we are talking about, O. This is a line joining C and O, and the O point is only accelerated towards the center of mass. Okay. For all of these points, this relation holds, but not for any arbitrarily accelerated point. Now, just imagine if there is only one couple. Or just couple moments. Okay. First off, that, since there is a couple, net force should be 0, right? So the acceleration would be 0. This is a true representation of the acceleration. Okay. But this representation, okay, the moment representation is with respect to a body-fitted coordinate system. Okay. That means the coordinate system itself is attached to the point O, this representation. Okay. So what is the meaning of this? In this sense, the object would be seen for those set of points. You see those fixed point and all that. So those set of points for a coordinate system that is fitted with O, it would seem that the object is performing rotation with this acceleration. Now, what is the amount of angular acceleration? That would depend on, of course, this part of the equation remains the same, the couple moment. This part will depend on the location of O. Okay, so the point is, it is little complicated to accommodate in today's class, okay, or this curriculum, so to be precise, okay, anywhere in this curriculum. So that's why dynamics of rigid body has been kept away from our curriculum, okay. But the thing is, net effect due to a couple is just the couple moment. Okay, that's the point we are trying to make, and that it can be thought of acting about any arbitrary axis which is parallel to the direction of this vector. Okay, so that is also valid. Okay.
স্যার যদি ফ্রি থাকে কোনো ফিক্সড পয়েন্ট না থাকে তাহলে সেন্টার অফ মাসের অ্যারাউন্ডেই ঘোরা উচিত না, মানে ইনটিউটিভলি তো তাই মনে হচ্ছে, কারণ মোমেন্ট অফ ইনার্শিয়াটা লিস্ট হবে ওখানে।
হ্যাঁ স্যার, হ্যাঁ।
Moment of inertia would be least about center of mass. Yes, that is true. But again, that would be as seen from a certain coordinate system. Okay. Anyways, even I'm not quite sure. I mean, what you are saying seems right.
মানে আমিও মানে ঠিক নিজেও কনভিন্স না যে লিস্ট মোমেন্ট অফ ইনার্শিয়াতে কেন হবে, মানে ইনটিউটিভলি মনে হচ্ছে, বাট আমি সলিড কারণ পাচ্ছি না যে।
So the thing is, I mean, what you are saying may also be right. Okay, and what I recall, I'm this is what the total expression turns out to be with all the conditions that I mentioned. Okay, so that is definitely true. I'm not sure about that least moment of inertia argument, but this definitely is true. But probably I'm missing something in this relation. I'm missing to give you something over here. So the thing is, it's not about which point is it trying to make a rotation. Okay, let's say it makes a pure rotation about the center of mass. Okay, but then with respect to some other point, okay, it could be thought of making a translation plus a rotation, right? I mean, if it is simply rotating about center of mass, let's say, then about any other point, it could be thought of translating and rotating. So, in that sense also, at times we find it really helpful to look at the motion not just from the center of mass but from a different point. For example, the compound pendulum that we talked about, more often than not, we find it more convenient to work with the pivot point, okay, than the center of mass. Okay, so pivot point, of course, comes under the category of fixed point. So, so the point is that even for that pivot point, if there was a couple acting on the body, the moment we should be taking into consideration, okay, is the moment due to the couple. Okay, so that's the idea. That's so if you're actually talking about the moment, then if there is just a couple, then it's the moment due to the couple. Okay, it's the same value. Okay, it doesn't matter whether you calculate with respect to center of mass or the pivot point. So you can use the same expression. Okay. Anyways, so let's move on to the problems. Okay, so in figure 44, what you see is this: there is this square block here, okay, and it is being tied down with a set of ropes, okay, which gives us a couple of 100 Newton forces forming a couple, and then there is another unknown force making an unknown angle theta. Why unknown force and unknown angle? It should not be unknown angle, right? Okay, so this is how the problem should be. Let's say that
এখানে তো দুটো ভেরিয়েবল হয়ে যাচ্ছে
let's say the angle theta is 20 degrees. Okay, then determine the value of P such that the net couple moment of the system is 0. Okay, so this 200 Newton forces would be giving you a couple, and this unknown set of forces P, okay, let's say they make angles theta, which is 20 degrees. Okay, so try to get the value of P such that the net moment should be 0, net couple moment. So essentially the net couple moment is sum of the two couple moments. কত আসছে p এর ভ্যালু? You see, you can use two ways. Primarily in your mind, it should be that I should take the 200 Newton forces and get the normal distance between the two. I would suggest simply take one of the points, let's say A is the point about which you are trying to get the moment. As we discussed earlier, you can get the couple moment about any point and you are going to get the same value. So why not take one point on the line of action of one of the forces? So take point A over here and try to
স্যার
get the
থিটাটাও কি আননোন?
sorry,
স্যার থিটাটা কি আননোন?
theta is 20 degrees. So take the position vector of B, which for a square should be 300i and 300j, because the angle is so the angle is given to be 45 degrees, so it's a square, right? So 300i, 300j, okay, and simply take the cross product. So determine the 100 Newton force at point B as a Cartesian component, as a Cartesian force vector. For example, you can do this. So if B is essentially this, no, sorry, it's 30 degrees, right? So this much, and then the position vector of B with respect to A is and simply you can get the couple moment is essentially
Sir, we can do the same thing for A, right?
sorry,
Sir, we can do
yeah,
this
you can do
entire
the,
thing with for A, means with respect to A.
or you are saying that take the position vector of A and take the cross product on the
For
force at
if
A.
A, for if A and R of A with respect to
Yeah,
B.
you are supposed to get the same value. If you
Yes.
if you are getting different value, then that's what there is a calculation mistake. So you can get the moment over here, and so you can, let's call it MC1, and similarly get MC2, which would be, let's say, R of C with respect to D cross FC. Okay. And the sum of these two moments should equate to 0. Of course, since the forces and the position vectors are on xy plane, the resulting moment would be along z direction. Okay, so the couple moment is in each case would be k cap, and don't forget to put the units. Okay, so 40% of you have already left. So we'll just do one more problem. So take theta equals 20 degrees. Okay. So can you get the value of P? Okay. So I guess you should be able to do that.
Sir, I am getting 106.578.
Sir,
P equals,
if we consider it 20 kilonewton, which was given, then it's 106.62.
sorry, what do you consider?
So in the problem they said 20, the total resultant.
No, that is for problem number 45.
Oh, actually I did that. Then it's coming 106.62 with if we consider 20.
Okay, okay. Okay. So if you consider that to be 0, what are you getting? Anyways, let's move on to the next problem. I hope you can understand this diagram. Again, three-dimensional.
So
So,
106.57 if we consider it 0.
okay, okay. So there is a pipe right here, which has double right angle bends. Okay. So the first bend takes place. So the first part of the pipe is along x-axis. Then the second part is on a plane parallel to YZ plane. Okay, and makes an angle of 30 degrees with the negative y-axis. Of course, that is normal to the first part, okay, which is along x-axis. Then the last part is again parallel to x-axis. Okay. So in that you can actually, there are 3 points A, B, and C. So there is a couple involving 50 Newton forces acting between C and A. Okay. These are three-dimensional problems, and yes, you can find out the normal distance between the two forces. Okay. Yes, and that distance is actually going to be this D right here.
Yeah.
Okay. So, and then you can find out what is the plane of the couple. Okay. And then you can, take components and all.
Yes.
But
Yes.
my suggestion would be, since we established that the cross product essentially is effectively giving us the moment due to a force, simply use a cross product. For example, if I were to calculate the moment due to the 50 Newton forces, I would simply be taking the position vector of C with respect to A, or for that matter B with respect to A, and taking a cross product with this minus 50I force. Similarly, for this 35 kilonewton forces, I'll be taking the position vector of B with respect to A, and then taking cross product with this 35K. Okay. So use cross product when you are calculating moment of any form. Okay, this point onwards, because we are dealing with three-dimensional problems, and chances of doing mistake by taking the normal distance and all, okay, is extremely high when we are doing three-dimensional problems. To find out the the direction or the unit vector of the product vector itself can be a challenge. Okay, so this problem statement here is, of course, the moment due to the two forces, two couples, Okay, there are two couples. Okay, so moment due to one couple is not in the same direction as the moment due to another couple. You have to understand that the moment due to the 35 kilonewton force is actually perpendicular, is along x direction, whereas the moment due to 50 newton force, okay, that is that moment is you know uh, is something between y and z. Okay, actually makes an angle of 30 degree with the z axis. Okay, so the point is that the two couple moments are not going to be along the same direction, but we want the absolute value of the moment, the absolute value. Okay, so when you sum all the couple moments, the net couple moment, the magnitude of that, we want that to be 20 kilonewton meter. Okay, and from that try to figure out the distance d. Okay, now at this point, if you have any confusion regarding the diagram, just let me know. Because we are talking couples here, we can actually try to get the moment due to all the forces about A, because two of them are actually passing through A. Okay, so that essentially is the moment due to all the couples right there.
Sir,
Yes.
sir, the resultant would be just the mod value, right? Of that entire moment vector.
No, the resultant couple moment. Okay, resultant couple moment is a Cartesian vector, but we want the magnitude to be that much.
Yes, mod value. Yes.
Yeah, 20 kilonewton meter. The magnitude should be that much. The resultant couple moment is in itself is a vector, but we want the magnitude.
Sir,
Yes.
if it is a kilonewton, then it is coming 342.05 meters.
342 point.
05 meters. 056. I got it.
Okay. 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 Then I probably made a mistake in posing the problem. That should be Newton meter possibly.
Yes, yes, I was also.
Okay. So as I can see that for that 50 Newton force, the normal distance is simply t, right? So 50d is the moment, net moment, and that moment would have a component along z-axis 50d times root 3 by 2. That is 25d root 3, and along y-axis it should be 25d, and the x component of the moment should be 35d root 3 by 2. So because the normal distance between the 35 kilonewton forces is d root 3 by 2. So along z-axis it is 25d root 3, along x-axis it is 17.5 d root 3, and along y-axis it is 25d. Is that what coming? What is coming?
So sorry, sir. Yes.
The net moment about net couple moment along x-axis it is 17.5 d root 3. Along z-axis probably 25 d root 3, and along y-axis possibly 25d.
Yes, sir. Yes, sir.
Okay, so the magnitude of all of that should be, let's say, 20 Newton meter. Okay.
Yes, sir.
Okay, so I think you can easily solve this problem, but just to be you just need to make yourselves comfortable with three-dimensional problem, and there would be a lot of them. Okay, going forward there would be a lot of them. So you would be solving 3D equilibrium problems. Okay, and even in 2D there would be complicated problems. So, and even in equivalent force system you will be solving a lot of 3D problems. Okay, so so let's meet on Monday, same time.